Hello everyone, I am Nikshita, MSc Chemistry student. It is audio recorded lecture of class 12th chemistry from NCERT book. Unit 3 Chemical Kinetics. Chemical kinetics help us to understand how the chemical reaction occur. Chemistry by its nature is concerned with the change. Substances with well-defined properties are converted by the chemical reaction into other substances with different properties. For any chemical reaction, chemists try to find out the feasibility of a chemical reaction which can be predicted by the thermodynamics and extent to which a reaction will proceed can be determined from the chemical equilibrium. Speed of reaction, that is the time taken by a reaction to reach equilibrium. Along the feasibility and the extent, it is equally important to know the rate and the factors controlling the rate of chemical reaction for its complete understanding. For example, which parameters determine it as how the rapidly food get spoiled, how to design a rapidly setting material for the dental filling, or which control the rate at which the fuel burns in the auto engine. All these questions can be answered by the branch of chemistry which deals with the study of reaction rates and their mechanism, called a chemical kinetics. The word kinetics is derived from a Greek word kinesis, means movement, and the thermodynamics tells only about the feasibility of a reaction, whereas a chemical kinetics tells about the rate of reaction. For example, the thermodynamic data indicate that the diamond shall convert it to the graphite, but in reality the conversion rate is so slow that the change is not predictable at all. Therefore, most people think the diamond is forever, and kinetic study not only help us to determine the speed or a rate of a chemical reaction but also describe the condition by which the reaction rate can be alternated, and the factors such as the concentration, temperature, pressure and the catalyst affect the rate of reaction. At the microscopic level, we are interested in the amount reacted or formed and the rate of their consumption and the formation. At the molecular level, the reaction mechanism involve orientation and the energy of a molecule undergoing collisions are described. In this unit, we shall be dealing with the average and the instantaneous rate of reaction and the factors affecting these. Some elementary ideas about the collision theory of reaction rates are also given. However, in order to understand all these, let us first learn about the reaction rate of a chemical reaction. Some reactions such as the ionic reaction occur very fast. For example, the precipitation of a silver chloride occur instantaneously by mixing of a aqueous solution of a silver nitrate and a sodium chloride. On the other hand, some reactions are very slow. For example, rusting of iron in the presence of air and the moisture. Also, there are reactions like inversion of cane sugar and hydrolysis of a starch, which proceeded with a moderate speed. Can be think of more examples from each categories. You must be knowing that the speed of an automobile is expressed in the term of change in the position or a distance covered by it in a certain period of time. Similarly, the speed of a reaction or the rate of a reaction can be defined as the change in concentration of a reactant or a product in a unit time. To be more specific, it is expressed in the terms of the rate of decrease in the concentration of any one of the reactant and the rate of increase in the concentration any one of the product. Consider a hypothetical reaction assuming that the volume of a system remain constant and R is changes into the P. 1 mole of the reactant R produces 1 mole of the product P. If R1 and the P1 are the concentration of the reactant and the product respectively at time T1, and the R2 and the P2 are the concentration at the time T2, and then delta T is equal to T2 minus T1 and delta R is equal to R2 minus R1 and delta P is equal to the P2 minus P1. The square brackets in the above expressions are used to express the molar concentration, and the rate of disappearance of the rate is equal to the decrease in the concentration of R and the time taken. That is equal to the minus of delta R concentration by delta T. Rate of appearance of the product. Increase in the concentration of a product is divided by the time taken is equal to the plus of the delta P concentration and are divided by a delta T. Since the delta R is negatively quantity and it is multiplied by the minus 1 to make the rate of reaction a positive quantity. Equation given above represent the average rate of reaction R average, and average rate depends upon the change in the concentration of reactants and the products and the time taken for that change to occur. Unit of rate of reaction. For example, from equation above, it is clear that the units of rate are the concentration time inverse. For example, if the concentration is in mole liter inverse and the time is second, then the unit will be mole liter inverse and the second inverse. However, in gaseous reaction, when the concentration of gases is expressed in the terms of their partial pressure, then the units of the rate equation will be the ATM second inverse. From the concentration of C4H9Cl butyl chloride at different times given below, the calculate the average rate of reaction. C4H9Cl plus water, C4H9OH plus HCl during different intervals of time. Time 0, 50, 100, 150, 200, 300 second, 400 second, 700 second or 800 second. We can determine the difference in the concentration over different intervals of time and thus determine the average rate of dividing, that is delta R concentration by the delta T. It can be seen in above that the average rate fall from the 1.90 into 10 0 की power minus 4 mole liter inverse second inverse to the 0.4 into 10 की raised to power minus 4 mole liter inverse second inverse. However, average rate cannot be used to predict the rate of reaction at a particular instant, as it would be constant for a time interval from which it is calculated. So, to express the rate at a particular moment of a time, we determined the instantaneous rate. It is obtained when we consider the average rate at the smallest time interval, says dt. Hence, the mathematically for an infinitesimal small dt instantaneous rate is given by the R average is equal to the minus delta R की concentration divided by में delta T is equal to the delta P की concentration by में delta T. At time at delta T is equal to 0, R instantaneous is equal to minus d R by में dt is equal to dp by में dt. It can be determined graphically by drawing a tangent at a time t on either of the curve of a concentration of R and a p versus time t and calculating its slopes. So in problem 3.1, R instantaneous at a 600 second, for example, can be calculated by plotting the concentration of butyl chloride as a function of a time. A tangent is drawn that touches the curve at time t is equal to the 600 second. The slope of this tangent gives the instantaneous rate. R instantaneous at the 600 second is equal to the 5.12 into 10 raised to power minus 5 mole liter inverse or second inverse. At time t is equal to the 250 second, R instantaneous is equal to 1.22 into 10 raised to power minus 4 mole liter inverse second inverse. At time t is equal to the 350 second, the R instantaneous is equal to 1.0 into 10 raised to power minus 4 mole liter inverse second inverse. And t is equal to the 450 seconds, R instantaneous is equal to 6.4 into 10 raised to power minus 5 mole liter inverse second inverse. Now we consider a reaction. Ag plus Cl2 is equal to HgCl2, where the stoichiometric coefficient of the reactants and the products are same, and the rate of reaction is given as the rate of reaction is equal to minus delta H G की concentration divided by delta T is equal to minus delta Cl2 की concentration by में delta T, or is equal to delta HgCl2 concentration divided by the delta T. That is, the rate of disappearance of any one of the reactant is same as the rate of appearance of the product. But in the following reactions, 2 mole of Hg decompose to produce 1 mole of each of H2 and I2. 2 Hi is produced H2 plus Ig. For expressing the rate of such a reaction where the stoichiometric coefficient of reactant and product are not equal to 1 and rate of disappearance of any one of the reactant or a rate of appearance of any product is divided by the respective stoichiometric coefficient. Since the rate of consumption of Hi is twice the rate of formation of H2 or I2, to make them equal, the term delta Hi concentration is divided by the 2. The rate of reaction is given by the rate of reaction is equal to minus half of delta Hi concentration by may delta T is equal to delta H2 concentration by may delta T. Delta I2 concentration by may delta T. Similarly, for the reactions, 5Br negative plus may Br O3 negative 6H positive changes into 3Br2 air plus 6 water molecules. Rate is equal to minus 1 by 5 of delta Br negative concentration by may delta T is equal to minus delta BrO3 negative concentration by may delta 2 and is equal to minus 1 by 6 of delta H positive concentration by may delta T is equal to 1 by 3 delta Br2 concentration by may delta T is equal to 1 by 3 delta H2O concentration by may delta T. For a gaseous reaction at constant temperature, concentration is directly proportional to the partial pressure of a species and hence rate can be expressed at the rate of change in partial pressure of a reactant or the product. Example 3.2. The decomposition of N2O5 in CCl4 at 318 Kelvin has been studied by the monitoring the concentration of N2O5 in the solution. Initially, the concentration of N2O5 is 2.33 mole liter inverse, and after 184 seconds, it is reduced to the 2.08 mole liter inverse, and the reaction takes place according to the equation. Calculate the average rate of this reaction in terms of hours, minute, and the second. What is the rate of production of NO2 during this period? Average rate is equal to half negative of delta N2O5 concentration divided by delta T is equal to 6.79 into 10 raised to power minus 4 mole liter inverse per minute. 4.07 into 10 raised to power minus 2 mole liter inverse per hour. 6.79 into 10 raised to power minus 4 mole liter inverse into 1 minute into 6 divided by 60 seconds. That is equal to 1.13 into 10 raised to power minus 5 mole liter inverse second inverse. It may be reminded that the rate is equal to 1 by 4th of delta NO2 concentration by may delta T. So the delta NO2 by my delta T is equal to 6.79 into 10 raised to power minus 4 into 4 mole liter inverse minute inverse is equal to 2.72 into 10 raised to power minus 3 mole liter inverse minute inverse. Factors influencing the rate of reaction. Rate of reaction depends upon the experimental conditions such as the concentration of reactant, pressure in cases of gaseous, temperature, and the catalyst. Dependence of the rate on the concentration. The rate of chemical reaction at a given time may be depends upon the concentration of one or a more reactant and the product, and the representation of a rate of reaction in terms of concentration of a reactant is known as the rate law. It is also called an rate equation or a rate expression. Rate expression or the rate constant. The result in above clear shows that the rate of reaction decreases with the passage of time as the concentration of reactants decreases. Conventionally, the rate generally increases when the rate of reactants concentration increases. So the rate of reaction depends upon the concentration of reactant. Consider a general reaction AA plus BB changes into Cc plus Dd, where the a, small b, and small c and d are the stoichiometric coefficient of the reactants and the product. And the rate expression for this equation reaction is rate is directly proportional to the concentration of A raised to the power x and the concentration of B raised to the power y, where the exponents x and y are may or may not be equal to the stoichiometric coefficient A and B of the reactant. Above equation can be written as the rate is equal to the k A की concentration raised to power x और B की concentration raised to power y minus d r की concentration y में dt is equal to k A की concentration raised to power x और B की concentration raised to power y. This form of equation is known as a differential rate equation where k is a proportionality constant called a rate constant, and the equation like which relates the rate of reaction to the concentration of our reactants is called a rate law or a rate expression. Thus, the rate law is the expression in which the reaction rate is given in terms of molar concentration of our reactants, with each term raised to the some power which may or may not be same at the stoichiometric coefficient of the reacting species in a balanced chemical equation. For example, N 2NO plus O2 is equal to 2NO2. We can measure the rate of this reaction as a function of initial concentration, either by keeping the concentration of one of the reactant constant and changing the concentration of the other reactant, or by changing the concentration of both the reactants. The following result are obtained. It is obvious after looking at the result then what when the concentration of NO is doubled and then that of O2 is kept constant and the initial rate increases by a factor of 4 from 0.096 to the 0.384 mole liter inverse second inverse. This indicates that the rate depends upon the square of the concentration of NO. When the concentration of NO is kept constant and the concentration of O2 is doubled, the rate also get doubled, and indicating the rate depending on the concentration of O2 to the first power. Hence, the rate equation for this reaction will be R rate is equal to K NO की power 2 or O2 concentration. The differential form of this rate expression is given as minus d R की concentration by mid dt is equal to K NO की concentration raised to power 2 O2 की concentration. Now we observe that for this reaction in the rate equation derived from the experimental data, the exponents of the concentration terms are the such same as their stoichiometric coefficient in the balanced chemical equation. Some other examples are given below. Reaction CH3Cl CHCl3 plus Cl2 changes into CCl4 plus HCl. Experimental rate expression. Rate is equal to K plus CHCl3 concentration and Cl2 concentration raised to the power 1 by 2. Second reaction CH3COO C2H5 plus H2O changes into CH3COOH plus C2H5OH, and rate is equal to the K and concentration of CH3COOH C2H5 raised to power 1 and the H2O concentration raised to power 0. In these reactions, the exponents of the concentration term are not the same as the stoichiometric coefficient. Thus, we say that the rate law of any reaction cannot be predicted by merely looking at the balanced chemical equation. That is the theoretical but must be determined experimentally. Order of a reaction. In the rate equation, rate is equal to K raised concentration of A raised to the power x and concentration of B raised to the power y. X and y indicates how sensitive the rate is to be changed in the concentration of A and B. A sum of these exponents, that is x plus y, is given the overall order of a reaction, where x and y represent the order which respect to the reactant A and B respectively. Hence, the sum of the power of the concentration of the reactants in the rate law expression is called the order of that chemical reaction. Order of a reaction can be 0, 1, 2, 3, and even in a fraction. A zero order reaction means the rate of reaction is independent to the concentration of a reactant. Calculate the overall order of a reaction which has the rate expression. Rate is equal to the K A की concentration minus 1 by 2 and B की concentration minus 3 by 2 and B rate is equal to K A की concentration 3 by 2 and B की concentration minus 1. Solution A rate is equal to the x plus rate is equal to the K A की concentration x or B की concentration y. So the order is equal to x plus y. So the order is equal to 0 and that is second order. And in case of B, order is equal to 3 by 2 plus minus 1 is equal to 1 by 2, that is half order. A balanced chemical equation never gives us true picture of how a reaction takes place, since rarely a reaction gets completed in one step and the reaction takes place in one step are called elementary reaction. When a sequence of elementary reaction gives a product and the reaction is called a complex reaction. These may be a conjugative reactions. Example, oxidation of ethane to the CO2 and H2O passes through a series of intermediate steps in which the alcohol, aldehyde and the acids are formed, and a reverse reaction and a side reaction. Example, nitration of phenol yield orthonitrophenol or pendaparanitrophenol. Unit of rate constant. For a Zernal reaction, AA plus BB changes into Cc plus Dd and rate is equal to the K A की concentration raised to the power x and B की concentration raised to the power y, where and x and y is equal to the n or number of order of a reaction and K is equal to the rate divided by the A की concentration raised to the power x or B की concentration raised to the power y. Concentration time divided by time multiply 1 by concentration की power n, where the concentration of A is equal to the concentration of B. Taking SI unit of concentration mole liter inverse and the time second, the unit of the K for different reaction order are listed in a table 3.6. Table 3.6 units of a rate constant, reaction order and the unit of a rate constant. Zero order reaction, order 0. So unit is equal to mole liter inverse second inverse. First order reaction order 1 and unit of rate constant is second inverse. Second order reaction 2, the unit of rate constant is mole inverse liter second inverse. Molecularity of a reaction. Another property of a reaction is called a molecularity, help in understanding its mechanism. The number of reacting species, atoms, ions, or a molecule taking part in an elementary reaction which must collide simultaneously in order to bring about a chemical reaction is called a molecularity of a reaction. The reaction can be unimolecular, which when one reacting species is involved, for example, decomposition of ammonium nitrate. NH4NO2 changes into N2 plus 2H2O. The bimolecular reaction involves the simultaneously collision between the two species, for example, dissociation of hydrogen iodide. 2HI changes into H2 plus I2. And trimolecular or a tetramolecular reaction involves the simultaneously collision between the three reacting species or a four reacting species, for example. 2NO plus O2 is changes into 2NO2. The probability that more than the three molecules can collide and react simultaneously is very small. Hence, the reaction with the molecularity 3 are very rare and slow to proceed. And it is therefore evident that the complex reaction involves more than three molecules in a stoichiometric equation must take place in more than a one step. KClO3 plus 6FeSO4 plus 3H2SO4 changes into KCl plus 3Fe2SO4 thrice plus 3H2O. This reaction will apparently seems to be of 10 times Tenth order is actually a second order, and this shows that the reaction takes place in several steps, and which step controls the rate of overall reaction. And the question can be answered if we go through the mechanism of a reaction. For example, chance to win the relay race competition by a team depends upon the slowest person in the team. Similarly, the overall rate of a reaction is controlled by the slowest step in a reaction called a rate determining step. And consider the decomposition of hydrogen peroxide, which is catalyzed by the iodide ion in an alkaline medium. 2H2O2 I negative in presence of alkaline medium changes into 2H2O plus O2. The rate equation of this reaction is found to be rate is equal to minus D concentration of H2O2 divided by m dt is equal to the K concentration of H2O2 or concentration of I negative. This reaction is a first order with respect to the both H2O2 and I negative. Evidence is suggested that this reaction takes place in two steps. H2O2 plus I negative changes into H2O plus IO negative, and H2O2 plus IO negative changes into H2O plus I negative plus O2. Both the steps are bimolecular elementary reaction. Species IO negative is called an intermediate since it is found during the course of the reaction but not in the overall balanced equation, and the first step begins slow and is the rate determining step, and thus the rate of formation of intermediate will determine the rate of reaction. Thus, from the discussion till now, we conclude the followings. Order of reaction is an experimental quantity. It can be zero and even or a fraction, but molecularity can not be zero or non-integral. Order is applicable to the elementary as well as the complex reaction, whereas the molecularity is applicable only for the elementary reaction. For complex reaction, molecularity has no meaning. Third, for complex reaction, order is given by the slowest step, and the molecularity of the slowest step is same as that of order of a overall reaction. Integrated rate equation. We have already noted that the concentration dependence of rate is called a differential rate equation. It is not always conventional to determine the instantaneous rate, as it is measured by the determination of slope of a tangent at point t in the concentration versus a time plot, and this makes it difficult to determine the rate law and hence the order of reaction. In the order to avoid these difficulties, we can integrate the differential rate equation to give a relation between the directly measured experimental data, that is the concentration at different times, and the rate constant. The integrated rate equation are different from the rate of a different reaction order. We shall determine these equations only for zero and first order chemical reactions. Zero order reactions. Zero order reactions means that the rate of reaction is proportional to the zero power of a concentration of a reactant. Consider the reaction R is converted into P and that the rate is negative dr की concentration divided by में dt, that is equal to K R की concentration raised to the power 0. At any quantity raised to the power 0 is unity, so the rate is equal to the K multiply 1. And del dr की concentration is equal to minus K dt, and integration both sides. R की concentration is equal to the minus Kt plus I, where I is the constant of integration. At time t is equal to 0, the concentration of reactant R is equal to the concentration R naught, where the concentration R is equal to R naught is initial concentration of a reactant. Substituting in equation, R naught is equal to minus K into 0 plus I. So the R naught is equal to I. Substituting the value of I in the equation, R की concentration is equal to minus Kt plus me R naught. Comparing with the equation of a straight line y is equal to mx plus c, if we plot a R concentration against time, we get a straight line with slope of minus k and intercept equal to the concentration of R naught. And further simplify equation, we get the rate constant k is as k is equal to the concentration of R naught minus the concentration of R and divided by time t. And zero order reactions are relatively uncommon, but they occur under special conditions. Some enzymes catalyze the reactions, and the reactions which occur on metal surfaces are a few examples of zero order reaction. The decomposition of gaseous ammonium on a hot platinum surface is zero order reaction at high pressure. 2NH3 changes into N2 plus 3H2. The rate is equal to the KNH3 concentration raised to the power 0 is equal to K. In this reaction, the platinum metal acts as a catalyst. At high temperature, the metal surface gets saturated with the gas molecule. So, a further change in the reaction condition is unable to alter the amount of ammonium on the surface of catalyst, making the rate of reaction independent of its concentration. The thermal decomposition of Hi on a gold surface is another example of a zero order reaction. First order reaction. In this class of reaction, the rate of reaction is proportional to the first power of a concentration of a reactant R. For example, reactant R changes into the product P. Rate is equal to minus d R की concentration by में dt is equal to k R की concentration. d R की concentration by में R divided by R की concentration is equal to minus dt. Integration this equation we get the ln R की concentration is equal to minus kt plus I. Again, I is the constant of integration and its value can be determined easily. When the time t is equal to 0, R is equal to R naught, where R naught is the initial concentration of the reactant. Therefore, equation can be written as a ln R naught concentration is equal to minus k multiplies 0 plus I. So ln R naught concentration is equal to 1. Substituting the value of I in the equation. ln R concentration is equal to minus kt plus ln R naught concentration. Rearranging this equation, ln R naught concentration R concentration divided by R naught concentration is equal to minus kt. K is equal to 1 by T ln R naught concentration by may R concentration. At time t1 for equation ln R1 is equal to minus kt1 is plus में ln R naught. At time t2 ln R2 is equal to minus kt2 and plus ln R naught, where the R1 and R2 are the concentration of the reactant at time t1 and t2 respectively. Subtracting above equation, ln R1 minus ln R2 concentration is equal to minus kt1 minus kt2. So ln R1 concentration divided by R2 concentration is equal to kt2 minus T1 and K is equal to 1 by T2 minus T1 ln R1 concentration by me R2 concentration. Equation can also be written as R ln is equal to the R concentration divided by R naught concentration is equal to minus KT. Taking anti-logarithm of both sides, R is equal to R naught E minus KT. Comparing equation with the Y is equal to mx plus c, if we plot a ln R against time t, we get a straight line with a slope of minus k and intercept equal to the ln R naught. And the first order reaction can be written in the form of k is equal to 2.303 divided by time t log R naught concentration by me R concentration. Log R naught concentration by me R is equal to KT 2.303. If we plot a graph between a log R naught divided by R V versus time, the slope is equal to K divided by 2.303. Hydrogenation of ethane is an example of first order reaction. C2H4 plus H2 changes into C2H6. Rate is equal to K concentration of C2H4. All natural and the artificial radioactive decay of unstable nuclei takes place by the first order kinetics. Decomposition of N2O5 and N2O are the some more examples of the first order reaction. Let us consider a typical first order gas phase reaction. A changes into B plus C. Let's Ppi be the initial pressure of A and Pt is the total pressure of at time t. Integrated rate equation for such a reaction can be derived as the total pressure Pt is equal to the Pa plus Pb plus Pc and pressure units. Pa, Pb, and Pc are the partial pressure of Pa, A, B, and C respectively. If X atoms atmospheric be the decreased in the pressure of A at time t and 1 mole of each of B and C is being formed, the increase in the pressure of B and C will be also be X atm exa each. A changes into B plus C at time t. Pi atmospheric pressure, 0 atmospheric pressure, 0 atmospheric pressure. At time t, Pi minus X atmospheric pressure, X atmospheric pressure at X atm, where Pi is the initial pressure at time t is equal to 0. P total is equal to the P initial minus x plus x is equal to the P initial plus x. So the x is equal to the P total minus P initial, where the P is equal to Pi minus x, Pi is equal to P total minus Pi. So the 2Pi minus Pt. K is equal to the 2.303 divided by time t log P initial by me Pa. So is equal to 2.203 time t log P initial minus divided by 2P initial minus P total. Half-life of a reaction. The half-life of a reaction is the time in which the concentration of a reactant is reduced to one half of its initial concentration. It is represented at the T half. For a zero order reaction rate constant is given by the equation. K is equal to the R naught concentration minus R divided by time t. At time t is equal to the T half, R concentration is equal to 1 by 2 of R naught concentration. The rate constant at T half becomes the K is equal to the R naught concentration minus half of R naught concentration divided by the T half. So the T half is equal to R naught concentration divided by 2K. It is clear that the T half for a zero order reaction is directly proportional to the initial concentration of the reactants and the inversely proportional to the rate constant. For the first order reaction, K is equal to the 2.303 divided by T log R naught concentration by me R concentration. At T half, R concentration is equal to the R naught by me 2. So the above equation becomes the K is equal to 2.303 T half log R naught concentration divided by me R concentration divided by 2. T half is equal to 2.303 K log 2. T half is equal to 2.303 K multiplied to 0.301. So the T half is equal to 0.693 divided by K. It can be seen that for the first order reaction, half period is constant and that is independent of the initial concentration of a reacting species. The half-life of a first order reaction is readily calculated from the rate constant and vice versa. For a zero order reaction, T half is directly proportional to the R naught concentration. For first order reaction, T half is independent of a R naught concentration. The order of a reaction is sometimes alternated by its condition. Therefore, there are many reactions which obey the first order rate law, although they are higher order reactions. Consider the hydrolysis of ethyl acetate, which is a chemical reaction between the ethyl acetate and the water. In reality, water affects the rate of reaction, but water is taken as a large excess of for hydrolysis. Therefore, the concentration of water is not alternated much during the reaction. Thus, the rate of reaction is affected by the concentration of ethyl acetate only. For example, during the hydrolysis of 0.01 molar of ethyl acetate with 10 molar of water, amount of reactants and the products at the beginning and the completion of a reactant are given under. CH3COOH C2H5 plus H2O changes into CH3COOH plus C2H5OH. T is equal to 0, 0.01 molar, 10 molar, 0 molar, 0 molar. T is equal to T 0 molar, 9.99 molar, 0.01 molar, 0.01 molar. The concentration of water does not get alternated during the course of reaction. So the reaction behave as the first order reaction, and such reactions are called as pseudo first order reactions. Inversion of cane sugar is another example of a pseudo first order reaction. Temperature dependence of a rate of a reaction. Most of the chemical reactions are accelerated by the increase in the temperature. For example, the decomposition of N2O5, the time taken for the half of the original amount of material to decompose is 12 minutes at 50 degrees Celsius or 5 hours at paramagnetate or oxalate acid and potassium paramagnetate get decolorized faster at higher temperature than at the lower temperature. It has been found that for a chemical reaction with rise in temperature by the 10 degree, the rate constant is nearly doubled. And the temperature dependence of the rate of a chemical reaction can be accurately explained by the Arrhenius equation. It was first proposed by a Dutch chemist G. N. Van Hops, but Swedish scientist Arrhenius provided its physical justification and the interpretations. K is equal to AE की power minus EA divided by RT, where A is the Arrhenius factor or the frequency factor. It is also called the pre-exponential factor. It is a constant specific to a particular reaction. R is a gas constant and EA is the activation energy measured in joule per mole. It can be understood clearly using the following simple reaction. H2 plus I2 is equal to 2Hi. According to the Arrhenius, this reaction can be takes place only when a molecule of a hydrogen and a molecule of a iodine chloride to form an unstable intermediate. It exists for a very short time and then breaks up to form two molecules of a hydrogen iodide. The energy required to form this intermediate called the activated complex is known as the activation energy. Is obtained by plotting the potential energy versus a reaction coordinate. Reaction coordinate represent the profile of a energy change when the reactant changes into the product, and some energy is released when the complex decomposition to form the products. So the final enthalpy of the reaction depends upon the nature of the reactants and the products. All the molecules in the reacting species do not have the same kinetic energy. Since it is difficult to predict the behavior of any one of the molecule with the precision, Boltzmann and the James Charles Maxwell uses statistics to predict the behavior of large number of molecules. According to them, the distribution of kinetic energy may be described by plotting the fraction of molecules with a given kinetic energy versus the kinetic energy. Here the Ne is the number of molecules with the energy E and the Nt is the total number of molecules. The peak of a curve corresponds to the most probable kinetic energy, that is the kinetic energy of a maximum fraction of a molecules. There are decreasing number of molecules with energy higher or lower than this value. When the temperature is raised to the maximum of the curve moves to the higher energy value and the curve beyonds out and it spreads to the right such that there is a greater proportion of a molecule with much higher energies, and the area under the curve must be constant since the total probability must be 1 at all times. We can mark the position of EA on a Maxwell-Boltzmann distribution curve. Increasing the temperature of a substance is increasing the fraction of a molecule which collides with the energy greater than a EA. It is clear from the diagram that is a curve at T plus 10, the area showing the fraction of molecules having energy equal to or greater than the activation energy get double, leading to the doubling the rate of reaction. In the Arrhenius equation, the factors E is minus EA divided by RT corresponding to the fraction of a molecules that the kinetic energy greater than the EA, and taking the natural logarithm of both the sides of equation. Ln K is equal to minus EA divided by RT plus Ln A. The plot of ln K versus the 1 by T gives a straight line according to the equation, and thus it has been found from the Arrhenius equation that increasing in the temperature and a decreasing in the activation energy will result in increase the rate of reaction and an exponential increase in the rate constant. Slope is equal to minus EA divided by R, and intercept is equal to ln A. So we calculate the EA and A using these values. At time temperature T1, equation is ln K1 is equal to minus EA divided by R T1 plus में ln A. At temperature T2, the equation will be ln K2 is equal to minus EA divided by R2 RT2 plus ln A. Since A is a constant for a given reaction, K1 and K2 are the values of a rate constant at temperature T1 and T2 respectively. Subtracting the equation from above, we obtained ln K2 minus ln K1 is equal to EA RT1 is equal to EA RT2 ln K2 by K1 is equal to EAR bracket 1 T1 minus 1 by T2 log K2 by K1 is equal to EA divided by 2.303 R 1 by T1 minus 1 by T2 log K2 by K1 is equal to RA 2.303 R T2 minus T1 divided by T1 by T2. Effect of catalyst. A catalyst is a substance which increases the rate of reaction without itself undergo any permanent chemical change. For example, MnO2 catalyzes the following reaction so as to increase its rate considerably. 2KClO3 in presence of MnO2 changes into 2KCl plus 3O2. The word catalyst should not be used when the added substance reduces the rate of reaction. The substance is then called an inhibitor, and the action of the catalyst can be explained by the intermediate complex theory. According to this theory, the catalyst participate in a chemical reaction by forming the temporary bond with the reactants, resulting in an intermediate complex, and this has a transfer existence and decomposition to yield the product and the catalyst. It is behaved that the catalyst provides an alternate pathway or a reaction mechanism by reducing the activation energy between the reactants and the products, and hence lowering the potential energy barrier as shown in figure. It is clear that the Arrhenius equation that the lower the value of activation energy, faster will be the rate of reaction. A small amount of a catalyst can catalyze a large amount of reactants. A catalyst do not have alter the Gibbs free, that is delta G for a reaction. It catalyzes the spontaneous reaction but do not catalyze the non-spontaneous reaction. It also found that the catalyst does not change the equilibrium constant of a reaction, rather it helps in attaining the equilibrium faster. That is, it catalyzes the forward as well as backward reactions to the same extent so that the equilibrium state remains same but it is reached earlier. Collision theory of a chemical reactions. Thought Arrhenius equation is applicable under a wide range of circumstances. Collision theory, which is developed by the Max Sturgers and the William Lewis in the 1916-18, provides a great insight into the energetic and the mechanical aspects of our reactions. It is based on kinetic theory of gases. According to this theory, the reactant molecules are assumed to be a hard sphere, and a reaction is postulated to occur when the molecule collides with each other. The number of collisions per second per unit volume of a reaction mechanism is known as the collision frequency. Another factor which affects the rate of chemical reaction is called activation energy. For a bimolecular elementary reactions, A plus B changes into the product, and the rate of reaction can be expressed rate is equal to Z ABE raised to power minus EA divided by RT, where ZAB represent the collision frequency of the reactant A and the B, and the E raised to power minus EA divided by RT represent the fraction of a molecule with energies equal to or greater than the EA. Comparing with the Arrhenius equation, we can say that the A is related to the collision frequency. Above equation predicts the values of a rate constant fairly accurately for the reactions that involves the atomic species or a simple molecule. But for complex molecules, significant deviations are observed, and the reason could be that of all the collision do not lead to the formation or product. The collision in which the molecule collides with the sufficient kinetic energy and the proper orientation so as to facilitate the breaking of bond between the reacting species and the formation of new bond to form a product are called as effective collision. For example, the formation of methane from the bromomethane depends upon the orientation of reactant molecule as shown in figure. The proper orientation of reactant molecule leads to the bond formation, whereas improper orientation make their simply bounce back and no product are formed. The account for the effective collision, another factor P is called a probability or a steric factor is introduced. It take into the account that the fact that is the collision molecule must be properly oriented. Rate is equal to the PZA B in e raised to power minus EA RT. And thus in a collision theory, the activation energy and the proper orientation of a molecules together determine the criteria for an effective collision, hence the rate of chemical reaction. Collision theory also has a certain drawbacks as it considers the atomic molecules to be a hard sphere and ignores their structural aspect. You will study details about this theory and more in other theories in your higher classes. Summary: Chemical kinetics is the study of chemical reactions with respect to the reaction rate, effect of various uh, variables, rearrangement of atoms, and the formation of intermediates. The rate of reaction is consonant with the decrease in the concentration of reactant and increase in the concentration of product per unit time. It can be expressed as instantaneous rate at a particular instant of time and the average rate over a large interval of time. A number of factors such as temperature, concentration of reactant, catalyst affect the rate of reaction. Mathematically represent the rate of reaction is given by the rate law. It has been to be determined experimentally and cannot be predicted. Order of a reaction with respect to a reactant is the power of a concentration which appears in the rate law equation. The order of a reaction is the sum of all the such powers of a concentrations of a terms for different reactant. Rate constant is the proportionality factor is the rate law. Rate constant and the order of a reaction can be determined from the rate law and the integrated rate equation. Molecularity is defined as only for an elementary reaction. Its values are limited from 1 to 3, whereas order can be 0, 1, 2, 3, or even a fraction. Molecularity and the order of a reaction are same. Temperature dependence of rate constant is described by the Arrhenius equation. EA corresponding to the activation energy is given by the energy difference between the activated complex and the reactant molecule, and A corresponding to the collision frequency. The equation clearly shows that the increase of temperature and the lowering of EA will be leads to the increase the rate of reaction, and the presence of a catalyst lowers the activation energy by providing an alternate path for the reaction. According to the collision theory, another factor P called a steric factor, which refers to the orientation of a molecule which collide, is important and contributes to the effective collision. Thus modified the Arrhenius equation to K is equal to PZA B e raised to the power EA minus EA divided by RT. Thank you.